Alright, so our last fundamental shape to talk about is a circle. So we probably already know the formula for the area of a circle is pi times the radius squared. But here we're going to try to understand why it is pi times the radius squared, and we're going to do that in terms of what we learned in the last video about regular polygons. So if you haven't watched that one, this probably won't make a lot of sense, but let's look at maybe a regular quadrilateral, aka square, and a regular hexagon that are roughly the same size. That wasn't too bad. And what I want to do is think about circumscribing a circle around these shapes, which I don't know how this will go. It's not the worst. Okay, let's see if we can center those up a little, maybe. That's a little better. This one could be a bit smaller. Not too bad. Okay, so the one thing I want us to get from this picture is the difference in area. So if I look at my circle and I look at my square, I have this difference in area is all of this green space. And then here, if I add up all of these green spaces, the sum is going to be less than it is for the square. And the more sides that I add, we saw this with polygons when we learned about them earlier, the more sides I add to a regular polygon, the closer it gets to being a circle. So if I made 12 sides or 20 sides or 100 sides, the shape looks more and more circular. And even though it's not a circle, it's still a polygon because it has straight sides, the more sides I add, the closer the area gets. This green area shrinks to be infinitely small if I add infinitely many sides. So what we want to do is think about the formula that we derived in the last video in terms of the way it is on like the star chart, which was the apothem times the perimeter over 2 is the area of a regular polygon. And what we're seeing with this relationship is if we add infinitely many sides, then the area basically becomes the area of this circumscribed circle. So in a circle, if we drew a triangle like that, just kind of like we had done here, we're talking about basically shrinking down this segment right here, this arc length, to be infinitely small, and we would get infinitely many triangles. So in terms of this formula, if I look at my circle, the apothem of a circle is the radius. So area is equal to the radius over 2, because we have this a over 2. And then my perimeter of a circle is 2 pi r. And that one is just definitional. So the way we defined pi was as a ratio of the diameter to the circumference. So 2 pi r is, by definition, the perimeter of a circle. It's the meaning, it's like what pi is. It's where it comes from. So if we kind of squish those together, the 2's cancel, and the r's square up to give us pi r squared. So a circle, the pi r squared formula, is basically the exact same formula that we were using for a regular polygon. It just, the radius is the same as the apothem, and the perimeter of a circle is 2 pi r. So I know you already know pi r squared, but hopefully this helps you appreciate kind of a way to understand it in terms of the things we've learned this year. Now, once we know the area of a circle, that allows us to talk about parts of a circle. So you may have done problems before where you did like a semicircle, like a half. That is, wow, that's so bad. I thought it was a trapezoid. Let's just use this circle. You may have done a half of a circle and found this area of a semicircle. And to do that, you just said, oh, well, that's half of a circle. So if a circle is pi r squared, it must be pi r squared over 2 is the area of a semicircle. But what we want to do here is extend our understanding beyond that and say that we can find the area of any wedge of a circle. So if I wanted to find just the area of, say, this orange wedge right here, then I can do that as long as I know the central angle, because the place this comes from, we said it's half a circle. So think of it the way we did arc length versus arc measure. If we said 180 degrees is half a circle out of 360 is the total, that's where that idea of 1/2 came from. But we're not limited to just 180. So let's say that this central angle here was 5 degrees. That means that 5 degrees out of 360 times the area, the whole area of the circle, pi r squared, is going to be the area of this orange wedge. And that wedge we call a sector. So a part of a circle's area is called a sector, just like a part of its circumference is called an arc. So if I take a wedge here, oh yeah, I'm still on that thing. Let me undo that. So if I take a wedge that looks kind of like an ice cream cone maybe, then this is an arc, this is a radius, and this inner part is called a sector. So really, sectors are just the same fraction of the area as arc length is a fraction of the circumference. So arc length over circumference is the same as sector area over total area of the circle. And that's going to be that ratio of the central angle over 360 is that ratio between those things. So yeah, now we know how to find the area of a circle and any part of a circle. So we can then use that going forward in our first actual lesson where we're going to do problems in this chapter, because we're going to be working with composite areas where we add or subtract several shapes.